everything started with the Big Bang, a point of essentially infinite temperature and energy. Hot, dense, and tiny is what the universe as we know it today started as. The beginning state, also known as the Planck era, lasted from 0 seconds to about 5 times 10 to the negative 44 seconds, according to Jones and Lamborn. Although we have no unified theory of everything necessary to describe the Planck era, we do know that the universe existed in an extremely hot and dense state. From then on, however, we have a fairly good idea as to what happened. According to Jones and Lamborn, from 10 to the negative 36 seconds to 10 to the negative 34 seconds, the universe went through a period of exponential expansion. This is called the inflationary epoch. During this inflation period, energy was released to form particle-antiparticle pairs, which resulted in most of the matter in the universe being created in almost an instant. After this inflation, quarks and leptons, along with their respective antimatter particles, were formed. These quarks and leptons were the original building blocks of matter, eventually forming electrons, neutrons, and protons. However, there was a slight imbalance between the matter and antimatter during this stage, with only around 1 matter particle per billion surviving. This is the reason our universe is predominantly made of matter today.
By 10 to the negative 12 seconds, all 4 fundamental forces, gravitational, electromagnetic, weak nuclear, and strong nuclear, became distinct, and there were quarks, leptons, particles, antiparticles, and photons all present. At 10 to the negative 5 seconds, quarks became bound to form protons and neutrons. At this point, if the matter and antimatter had been balanced, they would have annihilated each other. This means no stars, no galaxies, and no us. At about 1 second, neutrinos stopped interacting with other particles. Electrons and positrons began to disappear, and no new pairs were created. This electron-positron annihilation served 2 important functions. First, it distributed energy throughout the universe in the form of photons, and second, it led to the charge of an electron balancing the charge of a proton, resulting in an electrically neutral universe. During the first few hundred seconds, the extremely high pressure and temperature allowed for nuclear fusion to occur. This led to primordial nucleosynthesis, or the formation of low-mass elements such as deuterium, helium, and lithium. However, it would still take around 300,000 years for electrons to be captured in protons' orbit and form stable atoms.
According to PBS, 10,000 years after the Big Bang, most of the energy was in the form of microwave and radio radiation. As the universe expanded, energy was in equal parts of radiation and matter, which was now finally stable atoms. However, during the recombination epoch, the radiation waves were stretched and lost energy, resulting in faint cosmic microwave background radiation, which is a signature of the Big Bang. As stated by Jones and Lamborn, the first stars were born a few hundred million years after the Big Bang. The first step involved hydrogen gas cooling over time, coalescing into disks. The denser regions of these disks became star-forming clouds in which massive and luminous stars were born. These stars are identified as population 3 stars since they are made entirely of primordial gas and almost no metals. However, we would like to note that we have not found any direct observational evidence for the existence of population 3 stars. The current dominant theory is that all population 3 stars were of such high mass that they exhausted their fuel sources long ago. These stars were extremely massive, about 100 solar masses, and exploded into supernovae relatively soon after their formation. There is hope that the James Webb Space Telescope will be able to detect the faint blue light emitted from these earliest stars and the supernovae that they created. These explosions introduced metals to our universe, paving the way for population 1 and 2 stars to take form.
It wasn't long before galaxies started forming. Because of the link between supermassive black holes and galaxies, it was likely that their formations occurred simultaneously. There are 2 prevailing theories regarding the formation of the first supermassive black holes according to researchers at Caltech. The first theory, centered around stellar remnants, states that the early population 3 stars collapsed into intermediate black holes, and some of them were able to grow into supermassive black holes by consuming nearby gas. In addition, when stars went supernova, they released a lot of heat, thereby slowing the collapse of the galactic cloud. According to Cornell University, this created a cycle of collapse, star formation, and cooling that allowed for galaxies to take shape. Second theory, direct collapse, relies on the cooling effects of helium and H2 gas being suppressed, thereby allowing a cloud of pure hydrogen atoms to collapse into a supermassive black hole, skipping star formation entirely.
Either way, the formation of these first galaxies paved the way for the universe that we see today.